This is the Quantum Tech Pod, brought to you by Inside Quantum Technology, covering industry analysis, data, and market forecasting for quantum technology markets worldwide. Now, here's your host, Christopher Bishop.
Hello, everybody, and welcome to the Quantum Tech Pod. I'm delighted you're all listening. Good morning, good afternoon, good evening, depending on where you're sitting on the planet. My guest today is Pete Shadbolt, who's the Chief Scientific Officer at PsiQuantum. Pete's also a co-founder of PsiQuantum, which is a Palo Alto-based company building a large-scale, general-purpose silicon photonic quantum computer. As Chief Scientific Officer, Pete oversees the application and implementation of technology and scientific-related policies and procedures that are vital to the success of PsiQuantum. Pete earned his PhD in experimental photonic computing at the University of Bristol in 2014 and was then a postdoc at Imperial College London, researching the theory of photonic quantum computing. During his time at Bristol, he demonstrated the first ever variational quantum eigensolver and the first ever public API to a quantum processor. His company, PsiQuantum, is building the world's first commercially useful quantum computer, which they believe requires fault tolerance and error correction, and therefore at least 1 million qubits. PsiQuantum also believes photonics is the only path to building such a large-scale machine on a sensible time and money scale, and is using silicon photonics-based architecture that enables manufacturing in a conventional silicon chip foundry. We're going to talk about that. Worth noting that the team at PsiQuantum is a mix of quantum physicists, semiconductor systems and software engineers, as well as systems architects and more. So, Pete, welcome to the Quantum Tech Pod. Delighted you're here.
Likewise, thank you so much for having me.
So, Pete, I always like to start the podcast by asking my guests to share a bit about their own personal quantum journey, if you will. My objective certainly is to give our audience a sense of what you did before you founded PsiQuantum, but also to orient our audience to the fact that there are many ways and various paths that people have taken to get into the field of quantum information science. So can you please share with our listeners a bit about your background and path so far? Things like where you grew up. Tell us about your work at the University of Bristol and at Imperial College London, and maybe insight into any companies or universities or organizations where you worked before starting PsiQuantum.
So I've been working on quantum computing for about 10 years. Together with my co-founders, it's probably a combined 60 years of work on quantum computing prior to founding the company. Jeremy, our CEO, has been working on quantum computing for 25 years. It's really been his entire career. For me, myself, I started out actually working on the diametrically opposed approach to building a quantum computer, which is rubidium ions in ultra-high vacuum. So as an undergraduate and a master's student, I worked on floating rubidium ions in ultra-high vacuum, shooting them with lasers, and trying to build quantum information systems that way. And that's, of course, very appealing to physicists, and is kind of quite distinct from the manufacturable approach that we pursue here. And then I was very fortunate really to be in the right place at the right time. I went and joined Jeremy's group at the University of Bristol, also with Mark Thompson, who's one of the other co-founders here at PsiQuantum. And that was right at the point when they had just gotten started putting single photons into chips. So that research group at the University of Bristol was first team to take single photons, put them into telecom waveguides, and build qubits that way. So it's a very simple idea, which is to repurpose the photonics technology that's been developed over the last 25 years by the telecom industry. So they figured out how to lithographically fabricate waveguides on a chip, manipulate states of light with those waveguides. And then Jeremy and Mark were the people to say, let's put single photons in there. And that turned out to be a great idea. So I worked with that group for 5 years and saw it grow at a very rapid pace. And we had a fantastic time making small demonstrations of qubits, gates, and algorithms on a chip. So as you mentioned, things like quantum chemistry on a chip, controlled NOT gates, and a whole diversity of basic demonstrations of the science of manipulating photonic qubits.
Wow.
And so we did that for a while. and then I went to Imperial College. So I switched from being an experimentalist to being a theorist, and I went to work with Terry and Mercedes and Naomi, who now lead our architecture teams, on the math and the theory of how you build a fault-tolerant optical quantum computer. And at that time, a number of major breakthroughs were made in the architecture, and that really catalyzed the decision to found the company.
Wow. So thank you for sharing that. Great story. So the segue is, what led you to found PsiQuantum? Was there some epiphany? Tell me about the process. I want to say that I heard one of your co-founders and PsiQuantum CEO, Jeremy O'Brien, on a recent webinar describing the process. He said that you all left your cushy academic jobs and moved to Silicon Valley and burned the ships when you arrived. My takeaway was that's a pretty compelling statement of commitment, right? So how did you guys come together and decide to form this company?
Yeah, so I think that all quantum computing companies emerge from university research groups, pretty much. And they are all at risk of continuing to operate like university research groups. Some professor of physics within a successful experimental group gets to the level of maturity that they decide that it's right to start a company. And I think what was different with us and with PsiQuantum is that we really made a clean break from that academic mode of operation. So Jeremy and Mark in particular had gotten to a point in their careers where they could publish science and nature papers, with very high frequency. We'd shown the basic science worked many, many times, and we had kind of saturated the capacity of a university environment to make progress on the hardware. So all of the basic science worked, and on the architecture side, optical quantum computing had originally been something that didn't work. So prior to 2001, optical quantum computing was widely believed to be impossible because photons don't interact. The first disproof of that idea came in 2001 from Knilla, Flam, and Milburn, who showed that in principle, you could overcome that lack of interaction between photons and build a nominally scalable photonic quantum computer, but their proposal was extremely inefficient and completely impractical. And it took 15 years of sustained mathematical work by Terry and various other people around the world to turn that into something that was actually practical. And kind of the final nail in the coffin arrived in 2015. And that catalyzed the decision to say, there is no world in which you're going to build a machine of this scale and magnitude in a university. The right vehicle to build something like this is a private company. And that was the point at which we made a clean break and started something new. And I'm very glad that we did that.
Wow. So the opening copy on the website says that you guys are building the world's first useful computer.
Yeah.
So I have to confess that that's a pretty bold claim, given that competitors include companies like IBM and IonQ just went public, right, and Rigetti and even Google. So I want to get your take on why you think that is the case.
I think there's two. So first of all, let me agree with you. That is a bold claim. I'm excited to be working for a company that's trying to do something bold, right?
Yeah,
So
bravo.
I agreed. Let me first of all acknowledge that. I hope we still live in a society where you can try to do difficult things. The two words in there that are, of course, interesting are first and useful. And so let me start with useful. So what does it take to make a quantum computer useful? It takes 1 million qubits, as far as anybody knows today. 20 years ago, this was known. If you read Jeremy's PhD thesis from 20 years ago, he writes in the conclusion of that thesis that you're probably going to need about 1 million qubits to run useful algorithms on a quantum computer because of the need for error correction. In my undergraduate education at Leeds, which was excellent, by the way, during those introductory quantum information lectures, it was unequivocal. The only reason that we are talking about quantum computing, the only reason that you are studying quantum information is that the threshold theorem exists. It is known that you can perform quantum error correction. and suppress errors in a quantum computer. And so we have a hope of doing something useful with a quantum computer because of error correction. That was really the unequivocal narrative up until about 2015. So we worked on this variational quantum eigensolver idea, and there was a lot of other scientific work getting done at the time, like boson sampling, which generated the hope that you might get something done without error correction and with a dramatically smaller machine. And that was always a hope, but I think a lot of people really put their eggs in that basket in a serious way. They really, founded companies in some cases on the hope that you would be able to deliver something useful with 100 qubits and without error correction. And that was a completely defensible bet, right? We've now seen Google show an extraordinary scientific demonstration that I've been waiting 10 years to see, which is a chip the size of your thumbnail with 53 qubits on it that indeed wins races with a building-sized computer. That's an extraordinary demonstration of genuine exponential power. And the bet that you might have been able to do something useful with that in 2015 was a completely defensible bet, right? And in fact, today the jury is still out. It is still conceivable that we find something useful to do with such machines. But I think it is fair to say that the general optimism of the scientific community is diminishing as we've searched for 5 years and found nothing. So the story is still the same. You need 1 million qubits, you need error correction, and that's what we mean when we say useful. We mean a big error corrected quantum computer. And then the second word that makes that claim bold is the first. Of course, predicting the future is difficult, and I have great respect for my peers from competing organizations who would challenge that claim. But let me make an argument for why we actually believe that we will be the first. And I think the thing to emphasize is that it's not really a question of going faster. We have this approach which leverages semiconductor manufacturing. We feel very fortunate that because our qubits do not require exotic materials, atomic scale fabrication, millikelvin temperatures, etc., we are able to go to a tier one semiconductor foundry, which builds laptops and cell phones, has figured out how to build billions of components and leverage that extraordinary force to accelerate our roadmap. That's nice. That's very helpful. But really, the reason that we think we're going to be first is that the other approaches seem to have profound obstacles that may actually prevent them from reaching the necessary scale for usefulness, i.e. 1 million qubits.
Right.
So we could elaborate on that. But it's a bold claim, and I'll stand by it.
I want to shift gears and talk a little bit about funding for a minute. By the way, congrats on the Series D funding from BlackRock. Very exciting. But in reading about the funding situation or timeline, if you will, more interesting to me was the investment from Microsoft Corp's venture fund M12. Managing Director Samir Kumar said that PsiQuantum was the venture's first quantum computing investment. So I'd like to learn more about that relationship. So my question is, might we see a Quantum Surface Pro 50 at some point, or will there be connection to hardware?
Yeah, that's a great question. And first of all, let me just emphasize that it's an extraordinary privilege to be able to work on a technology that is, as exotic and novel as this, and to work in an environment where you can actually fund a project that is, of course, unequivocally a moonshot technology. So that's really an extraordinary set of circumstances to find myself in, and I feel very privileged to have that support. And then you ask about Microsoft. So Microsoft actually came in at Series C, and they've invested again into this Series D round. And we have always had a great relationship with the Microsoft team, principally because of their extraordinarily strong technical team and their ideology about how you should build a quantum computer. So first and foremost, Microsoft have understood from the very beginning that you're going to need error correction. and they've taken it extremely seriously. That's in two respects. So first of all, on the hardware side, they've pursued an approach that recognizes that you won't get something done with typical physical error rates. So they understood that you're not going to get anything done with a 0.1% error rate or something. And so they pursued a hardware approach, attempted to mitigate that. And I think it's fair to say that they pursued a very high risk, very high reward approach on the hardware. And I think that's a completely defensible bet. Then on the software side, on the algorithm side, Microsoft is extremely distinguished in having been one of the few groups in the world who has actually done their homework on fault-tolerant resource counting. So there are a ton of people running around the world saying that quantum computing is going to change your industry. There are very few people who can actually support those statements, because to support those statements, you have to calculate how long it is going to take your quantum computer to run a known algorithm for a useful problem size. And that calculation involves very involved analysis of the fault-tolerant gate sequences that you have to generate to run that algorithm, and typically involves a whole bunch of very delicate optimization of those gate sequences. And that's homework that most people haven't really bothered to do. Microsoft has really done that in a serious way. And so the few examples that the world has of properly accounted applications for quantum computers, a good fraction of those come from that Microsoft group. So let me just summarize. And they've just been very serious about quantum computing for more than a decade. So yeah, that's a fantastic relationship. We really appreciate their perspective on, where the priorities actually are. Of course, we pursue a different approach on the hardware side, but that's fine.
So let's talk. So segue to follow the thread around software. So let's talk SDKs, right? Are there
Yeah.
limits to the kinds of tools that developers can use to write algorithms for a photonic computer? And or the following question, like, are you writing your own software or engaging with partners for this? How does that work at PsiQuantum?
Yeah. So you asked, first of all, are there constraints or idiosyncrasies specific to photonic? And then you asked whether we have our own SDK. So as far as constraints and idiosyncrasies, to first order, the answer is no. We're building a universal fault-tolerant quantum computer with a textbook universal gate set, which you would program in exactly the same way as any other textbook quantum computer. So you've got, your Toffoli gates and your CNOT gates and your T gates and the standard set of gate operations. And yeah, so it's a vanilla textbook machine from a programming point of view.
Okay.
There are some optimizations that you can make in the lower level code that takes into account the fact that this is a photonic machine. There are things that you can do with photons, like move them around over long distances, that in some cases give you an advantage. But yeah, to first order, it's a textbook quantum computer, and you shouldn't have to worry about the fact that it's photons under the hood. As far as SDKs, yeah, we have a SDK. You can program it in Python, JavaScript, C++, and we have it in the hands of some of our customers.
Back to hardware for a second. So I read that PsiQuantum struck a deal with Global Foundries that was announced in May to build quantum chips at their manufacturing facilities. And I don't think we can understate the potential impact of having a strategic relationship, right, with one of the largest chip fabs in the world. So you're now manufacturing quantum photonic chips as well as the cryogenic CMOS chips that are needed to control the qubits. So share with our listeners how this will give you a competitive advantage when it comes to building, say, a million qubit quantum computer. And do you see yourself selling these chips maybe to hardware vendors at some point?
You're right. It is strategically and practically extremely important for us. And actually, we've been working with Global Foundries for more than 2 years now. And the thing to emphasize, some people appreciate this, but it's a little bit of an esoteric characteristic of our world, which is that you've got to put the qubits on a chip, just practically speaking. There's lots of factories around the world that can make a chip In fact, if you want to, you can make chips in a university clean room. There's thousands of small R&D oriented semiconductor foundries that will make chips for you. But the underappreciated reality is that there are really only 3 tier 1 semiconductor foundries on the planet. Those are TSMC, Global Foundries, and Samsung. Intel is a special case. Intel got out of the foundry business. They're getting back in. I should probably add them to that list. But the capability of those commercially oriented tier 1 foundries is massively distinguished from everything else. And that's not only in terms of their ability to build chips in large volumes and at low cost. It is much more importantly in terms of the process control, CD uniformity, line edge roughness, basically their ability to fabricate devices with incredible precision and control. And when we founded the company, we knew from the very beginning, if we want to build millions of devices whose performance meet the stringent requirements of fault tolerance, we would need to build those devices in a tier 1 production line. Now, that, of course, is challenging given that TSMC, Global Foundries, Samsung are not in the business of doing crazy science fiction stuff like quantum computing.
Right.
And so it's been a huge effort for this company and a huge milestone to have taken, honestly, quite exotic quantum devices like single photon detectors and to have now taken that technology to the level of maturity where we can build them in very large numbers, shoulder to shoulder with laptops and cell phones in that mature semiconductor manufacturing context. So yeah, we're very proud of that. It's a really, key component of our strategy, and it is paying off as far as we can tell.
Yeah, fantastic. So let's talk a little bit more about the technology. I have a couple questions. I read that PsiQuantum has created a more efficient waveguide, which is used to route photons inside the chip without giving away competitive advantage. Can you describe that a little bit? How that
Yeah,
works?
so that's one example of many, many components that go into the system. The waveguide is a good example to illustrate why you go to an expensive manufacturing line like Global Foundries. If we wanted to keep things really simple and keep our costs super low, we would go to a small R&D oriented, mom and pop type R&D foundry and make a few chips. The problem is that we need very low loss, so we don't want to lose any photons out of the waveguide. And the main way that photons go missing is that you have edges on those waveguides that are not straight. You get some wiggles on the edge of the waveguide, roughness basically. And if you have that, then photons don't stay in the waveguide. They fall out the side. They go missing. And that's actually the primary source of error in a photonic quantum computer is photons go missing. And so it's really a very mundane, practical semiconductor process problem, which is that you want really straight lines. You want super low line edge roughness. And there is then an economic factor, which is, well, who's spent the most money on the most expensive tools to make really, really straight lines? Well, it's the big factories, right? So we
Yeah,
have to go
right.
there. And so it's pretty simple. Like it's not in the instance, we do have advanced devices like single photon sources and detectors and so on, where we have a lot of design IP and where we do a lot of simulation to optimize the performance of those devices. In the instance of the waveguide, without diminishing the design work that goes on there, the single biggest factor is really, did you use an expensive tool or not? And so we do use expensive tools, and therefore we have efficient waveguides. And that's a very mundane but extremely important component of what we're doing. Yeah, does that make sense?
Yeah. No, thank you for calling that out. Very interesting. One more kind of granular in the weeds question for our listeners. In January of this year, you guys posted to the archive an article introducing what you called fusion-based quantum computing, FBQC is the acronym, a model of universal quantum computation in which entangling measurements called fusions are performed on the qubits of small, constant-size entangled resource states. It says you're using a stabilizer formalism for analyzing fault tolerance and computation. Can you tell listeners more about this and how it might be applicable, maybe certainly within PsiQuantum, but maybe more broadly, right? If it's a universal quantum computation model.
PsiQuantum hasn't published many papers, and that's because we're a company, not a research group.
You've left academia behind.
We've left academia behind for very good reason, which is that we're interested in actually building a working machine in a hurry.
Yeah.
Fusion itself is an idea that we've had in the literature, well before we founded the company. So Terry cooked up that idea, and it's a very simple entangling operation that is not a controlled NOT gate. So the basic entangling operation that we use in photonics under the hood is not a controlled NOT gate. Per our previous discussion, we then synthesize the conventional universal gate set at the fault-tolerant level using entangled states that are constructed via that unusual entangling operation of fusion. And so, prior to founding the company, we had Terry and Mercedes and many other people who work here and elsewhere had described a whole diversity of different approaches to the network that you would require to implement fault-tolerant optical quantum computing.
Right.
One of the most important aspects of such an architecture is the optical depth. Naively, if you think about how you might build a photonic quantum computer, what you might imagine is that you're going to generate single photons. You're going to use those photons to encode qubits, maybe in a polarization encoding or in a path encoding as we use on a chip. And then you're going to fly those photonic qubits through a sequence of optical widgets where each widget encodes a gate or an operation that you're trying to do on the computer. So you can imagine this, huge long chain of optical widgets.
Yeah.
You're going to fly these photons through that chain. They're going to come out at the far side. You'll measure them and read out the state of the quantum computer. That's a very natural construction, but it has a very serious problem, which is that no optical widget is perfectly transparent. And so the chance that you get light through a billion optical widgets is nil, right? No light is going to come out the other side. If you imagine a stack of pieces of glass, if you've ever stacked glass, it very rapidly becomes a mirror. And so that's a profound problem. In fact, what you need is an architecture in which the optical depth, meaning the number of components that the photon traverses in its lifetime, is constant, small, and independent of the problem size. So as you add more qubits or add more gates to the computation, you can't add more widgets into the path of the photon. And that might seem to be an impossible task. It really seems like a paradoxical requirement. I want a machine where I can run an arbitrary number of serial gate operations, but where the number of components that a photon traverses in its lifetime is fixed and independent of the problem size. And FBQC does that. It is not the first architecture to do that. There were architectures prior to FBQC that meet that requirement. And in fact, Mercedes' PhD thesis, which is part of the founding architecture of the company, meets that requirement. What FBQC really does is to do that much more efficiently than we had previously been able to do. It's a pretty high-level summary of some of the aspects of the architecture that we pursue. And I would like to emphasize that the level of depth in that paper on the archive is minuscule relative to the sophistication of architectures that we actually develop and pursue inside the company. So we wanted to put something in the public domain that showed the basic characteristics of what we're trying to do. It's important people can look at what we're thinking, but one should also not get the impression that that is the architecture that we pursue.
Thank you for explaining that. Appreciate it.
Sure.
I want to shift gears and talk policy for a moment. I know that PsiQuantum was among an elite group of companies invited to participate in the White House Summit in early October on quantum industry and society. I want to get your take on, what you took away, what the company took away from that conversation, particularly as regards where we are in terms of government support as well as collaboration across the private sector and academia.
Yeah, it was a great privilege to be invited to that event. And I think it was an extremely well organized, well intentioned, successful event. The biggest takeaway for me from that event is that when we founded the company, it was really quite an extreme choice for us to say that we exclusively targeted a fault tolerant machine with 1 million qubits.
Yeah.
The status quo in 2015 was to found a company where you would tell venture capitalists that you hoped to deliver something useful with a NISQ machine, and that you were going to build a machine that's about 10 times bigger than what you had in the university, and that maybe at some point in the future you would do error correction, but we're going to, deliver value with NISQ was kind of I think it's fair to say, like the prevailing approach. And we were pretty, we were certainly like an outlier in just sort of bluntly stating that you need 1 million qubits in error correction. Frankly, explicitly dismissing NISQ as a strategy. And 5 years later, it is awesome to be at the White House and to have Microsoft, Intel, Google, HRL, etc., one after the other, explicitly stating you need 1 million qubits, you need error correction. Right?
Yeah, you were right all along, oh brother.
Yeah, I mean, I want to go and find my old lecturer from Leeds and tell him that story. That's I think extremely healthy for the industry. I think that been a long time coming, but the whole industry is now facing up to that reality. You need a really big quantum computer, and I think it's only healthy that people are then starting to seriously invest in the non-quantum challenges that raise their head once you recognize that that is the requirement. And those non-quantum challenges are things like manufacturability, which of course we've spent a lot of time and money on, cooling power, connectivity, control electronics. You see these themes now emerging in a serious way and being taken seriously by these other organizations. I think that's extremely good for the industry, and just the clear understanding from the government side that quantum computing is potentially a technology that has profound strategic importance, and there's very clear support and recognition of that.
We've come to what I call sort of the inevitable $64,000 question, which is quote unquote clients. Right. So I read that PsiQuantum has customers in sectors ranging from healthcare to electronics and transportation, and that they're exploring use cases and algorithms for quantum computing. And I realize you may not be able to identify specific clients unless you want to white label or anonymize them, but can you give us a sense of the kinds of work you're doing for them and maybe where you're getting traction initially, like what verticals are adopting and understanding the power of this technology?
Yeah, so the verticals that you mentioned are exactly right. So transportation, won't surprise anybody to hear that we work on lithium-ion battery chemistry problems. Pharmaceuticals, drug design, we work on materials design, we work on some financial applications, the kind of the pretty well-known applications for quantum computing. There are a few outliers, but it's no surprise to anyone that we work with whatever Fortune 500 type companies on those problems, and we are delighted to have a growing roster of customers who are not only enthusiastic about working on quantum computing, but also increasingly technically serious about it. So it's been fantastic to see these large corporations hiring PhDs in quantum information, building teams, and really getting organized around what they're going to do with a quantum computer when it arrives. And in terms of what we actually do with them, what we don't do is take a 10 qubit chip, hook it up to AWS, and make it available to our customers.
Fair enough. Yeah. Yeah.
I think it's extraordinary that we live in a world where high school students, undergraduates, whatever, can pay a small amount of money or not and get access to a real quantum processor. I think that's awesome. I think, like, pedagogically, for people who are learning about quantum computing, that's a huge, service to the world and tremendously exciting. Like, you can really sit in your living room at home and get access to some entangled qubits. Like, that's incredible. On the other hand, our customers, in the majority of cases, I think it's fair to say, have done that. They've gone and played around with a handful of qubits online. And I would say that they really learn two things from that. The first thing they learn is it's real. Like, there's nothing fake. The qubits are entangled. We can run gates on them. And the second thing that they learn is we're going to need like millions of qubits, billions of gates, error correction, fault tolerance. And so that's the context in which most of our customers come to us. And so what we actually do is we don't touch the hardware because it doesn't work yet. And instead we do math and we do fault-tolerant resource counting. So we take those applications that customers care about and we do the, in many cases, pretty involved and time-consuming work of figuring out whether or not those use cases can achieve a meaningful quantum advantage on a fault-tolerant quantum computer of the type that we're building. And as far as we're concerned, that's a useful output, right? Like, if you again, there are very, very few algorithms where people have really done this homework. And I think it's pretty weak to live in a world where you say, I reckon quantum computing is going to be awesome. Like, you got to answer the question. You got to actually do your homework and be able to say, yes, we are absolutely certain that if we were to run this code here on a machine with 1,300,225 physical qubits and a logical error rate of whatever, we would get an answer to this specific problem in an hour and 25 minutes. And that problem is not ever going to be solved on any conventional computer. Making statements of that kind of concreteness and defensibility, I think that's really valuable and worth doing. So that's what we do with our customers. Yeah.
Yeah, great. So Pete, we're coming to the end. I always like to close my podcast with questions about a topic that I'm passionate about, which is workforce enablement, right? So I want to get your take on the challenges facing a company like PsiQuantum in finding talent. Like, since you guys are in the South Bay, it has to make it easier to some degree. You're near Stanford and UC Berkeley, so
Yeah.
big schools are nearby, as well as large talent pools you could, in theory, poach from Google or Facebook or Twitter or myriad other startups. But can you tell me a little bit, even at a meta level, about the recruiting process at PsiQuantum and what the challenges are that you guys face?
Yeah. So we founded the company here in Silicon Valley, despite all four of the founders being British citizens and living in the UK, because we thought this was the best place to start it. And we still think that is the case. We have the majority of our team here in Silicon Valley, but we also have a growing number of people all around the world. I think so you hear a lot about challenges of finding talent in quantum computing. I think we are a little distinct in that respect, in that a large fraction of the people that we need to do the work are not quantum people at all, because we're not really developing we're not really going back to our previous discussion, right? What's stopping us from delivering a quantum computer? Well, one of the things that we need to improve is loss. How do you improve loss? Well, you need to reduce your lineage roughness. You need to make less wiggly lines. Is that a problem for which you need a PhD in quantum information or experience programming a 10 qubit quantum processor? Categorically, no. That's a task for which you want somebody with serious semiconductor manufacturing experience, of which, of course, there are lots of people in the Valley and elsewhere. So I don't want to downplay the challenges. We hire lots of PhDs in quantum information, experimental quantum optics people, cryogenics people, you name it, superconducting device people. And finding those people is challenging. But I would also say that PsiQuantum has a slightly unusual profile in that we are heavy on non-quantum people also.
Well, thank you, Pete. This has been a great conversation. I want to close by inviting people to follow you on LinkedIn. Point them to your website, right? It's PsiQuantum.com. You have a Twitter handle as well, at PsiQuantum.
Yeah, the Twitter is great. If you check out our Twitter account, it's like one of the best Twitter accounts going.
Cool.
Absolutely. Yeah.
Okay. Well, that sounds great.
I'm joking.
And
There's nothing on it.
you're joking. There's nothing on it. Okay. Well, I saw that you do have a handle. So,
Yeah.
what about a group on LinkedIn? I mean,
Yes, I think there is some content on LinkedIn. Yeah.
yeah. Okay. Again, just to encourage people to connect with you and the company and learn more about what you're doing. So, Pete, thanks for joining me today, and thanks to all of you for listening. It was a great conversation. I enjoyed it.
Likewise, it's a real pleasure. Thank you so much for taking so much of your time, and really appreciate it. Yeah, thank you.
No, you're very welcome. Delighted to speak with you. Thanks again, Pete, for joining me today. Thanks to all of you for listening. Please share this podcast on your social media channels to increase the impact of my conversation with Pete, increase awareness of what PsiQuantum is doing, their innovative approach to photonic quantum computing. Listen to my other podcast episodes if you haven't already. Please connect with me on LinkedIn. I want to mention that this has been a production of Inside Quantum Technologies.
You've been listening to the Quantum Tech Pod, brought to you by Inside Quantum Technology. For more information on this episode or other topics relating to quantum technology, visit InsideQuantumTechnology.com.